Hello everyone. Today we are going to study hypothesis testing and also we are going to study p-value, which is one of the important concepts in statistics. All right. Before we directly go into this material, I'm going to talk about a little bit about basic statistics. All right. Usually, statistics is classified into two. Okay, one is called inferential statistics. Okay, the other one is called descriptive. Okay, descriptive statistics is about summarizing data by using graphs or numbers like a mean, right? In this semester, we are going to focus on inferential statistics, right? So, what is inferential statistics? Suppose that we have a population here. Okay, this is population. We want to know something about population, right? For example, population mean is denoted as mu. Okay. Now, you know that it is very hard or difficult to measure, these things, right? Population parameter. So what we do is take samples from this population, right? So small sample, and then you compute, sample statistic, right? So in order to know something about mu, you usually take a sample from population and you compute the sample mean, right? And then you infer by using this sample mean, you infer something about population parameter, right? That's inferential statistics, right? So when you do this, you usually set up hypothesis, right, about the population parameter. So for example, we'll talk about this one today. Usually the hypothesis comes in pairs, right? One is called the null hypothesis, and the other one is called the alternative hypothesis, right? So this one is null hypothesis, and this one is alternative hypothesis, right? So for example, you can set up a hypothesis like mu is greater than 50. You usually use equal sign here, right? You set up hypothesis like this, and then you want to test this hypothesis, right? So in order to test this one, so you take sample and you compute x bar, right, sample mean, and if sample mean turns out to be greater, let's say this one is about 60. In that case, you can conclude that you reject null hypothesis because x bar is 60, then it is very likely that this one is supported, right? So you reject null hypothesis, right? What about the case where we have x bar turns out to be 35, right? Then you accept null hypothesis, right? Now, the problem of this is that what happens if x bar turns out to be, let's say, 51, right? Then it's very difficult to make a concrete conclusion, right? So it's we are going to deal with this type of a situation where it's very hard to make decisions, right, about the hypothesis, right? Actually, when you make this type of conclusion, you have to set a value called alpha, right? So we'll talk about this one later. This one is called the significance level, right? When you read research papers, right, you usually see alpha is 0.05 or 0.01, right? So we'll talk about this one when we go into the hypothesis testing, right? Now, another example. Suppose you wanna show that there is a positive relationship between variable x1 and variable y. Okay, I'm talking about the situation where we have regression. So, for example, you have equations like this. By the way, the regression. So, what is regression? Regression is to find the relationship between independent variable and dependent variable, right? So, finding the relationship means what? So, you want to check the coefficients, like beta 1, beta 2 here, right? So, you can set up hypothesis like this. If you want to show there is a positive relationship between x1 and y, you can set up like this. Okay, beta 1 is greater than 0. Right? Or if you want to show that there is a positive relationship between x2 and y, you can set up hypothesis like this, right? And what you want to do in order to test, this hypothesis, right? You get the data, and you find the estimates, okay, from sample data. Okay. Now you want to check, whether these ones. If B1 turns out to be positive, then you reject these things, right? And if B2 turns out to be positive, you reject this one, right? So this type of things is called inferential statistics, right? So we are going to study hypothesis testing today. Now let's go into the hypothesis testing. As I said, hypothesis comes in pairs. One is called the null hypothesis. Usually we denote this one as H0, right? And the other one is called the alternative hypothesis, okay? Sometimes this one is called the research hypothesis, right? This one is denoted as HA or H1, right? Remember that this alternative hypothesis is more important than the null hypothesis, right? Because this hypothesis is the one that you want to support, right? The hypothesis that you write in your paper or your thesis is the alternative hypothesis, right? Usually. So this one is the one, I'm going to repeat it. So this hypothesis is the one that you want to support, right? So for example, if you want to, show that there is a positive relationship between A and B, that's the hypothesis that you specify in your paper, right? That's your alternative hypothesis. So that means what? So this one is the one that you want to support, right? So, when you do the research, you want to reject the hypothesis, right? This means you support, accept H1, right? Let me say it again. So if you want to support something, right? So you put that hypothesis in the alternative hypothesis, right? Now, there are three types of hypothesis, okay? One is you have inequality like this, okay? And another one is you have an inequality like this. And the last one, you have a not equal here, right? Usually, this type of hypothesis is the default hypothesis in the statistical package, right? So you usually do the two-sided test, okay? This one is two-sided test is used, for example, in regression. Remember that so if you have a regression equation like y is beta 0 plus beta 1 x1 beta 2 x2, right? So you want to check whether there is a positive relationship between x1 and y. You can set up hypothesis like beta 1 is greater than 0, right? But in the statistical package, right, what the package does is to set up hypothesis like this. Right? So usually, the computer, the statistical package set up hypothesis like this, two-sided test, right? Now let's talk about the making conclusions about the hypothesis, right? So your conclusion should be like this: either do not reject null hypothesis or reject null hypothesis, right? This one means what? So you reject, in this case, you reject alternative hypothesis, right? In this case, you accept alternative hypothesis, right? So if you reject null hypothesis, that's good news because you are accepting alternative hypothesis, which you support, right? Okay, now let's go to the whole process of doing the hypothesis testing, okay? Oh, before we do that, let's talk about the concept called the type 1 error, right? Remember that you have to set the alpha value, right? Alpha is called the type 1 error. Okay. Alpha is the usually 0.05 or 0.01, right? The alpha is the probability that rejecting null hypothesis given that null hypothesis is true. So alpha is kind of a conditional probability, right? So rejecting probability of rejecting null hypothesis given null hypothesis is true. So that means what? That's making error, right? So alpha is the probability of making error, right? So when you do the hypothesis testing, there is always a possibility of making errors because there exists always the sampling error, right? You are taking samples from population, right? And then you compute the sample statistic, right? So you using the sample statistic, you infer something about the population, right? So in that case, there is always a possibility of making errors, right? So you have to set the level of making errors, right? Now let's go through the hypothesis testing procedure, right? So you set up hypothesis first, okay? And then you need to set the significance level alpha, right? Usually this one is 0.05, 0.01, right? And then you need to compute test statistic, right? I'll talk about this one when you do the actual example, right? So you take sample and for the hypothesis about the mu, right? You compute the you take sample and then you compute X bar, right? And then you transform this one to you standardize this, right? That's called the test statistic, right? You transform this one to z value or t, right? That's called the test statistic, and then you determine the rejection rule, okay? And then you actually gather data and compute test statistic, and you make conclusions, right? That's the procedure, right? But this is the procedure for doing the hypothesis by hand, right? Actually, the computer doesn't do this, right? So computer only gives you the p-value, right? And then once you get the p-value, you can make conclusions about your hypothesis, right? We'll talk about that after going through, this step, right? Now let's talk about the this hypothesis first, right? Suppose you have inequality like greater than in the alternative hypothesis, right? And suppose you set the alpha as 0.05, okay? Usually, this is the case because this is a default value in the statistical package, right? And your test statistic in this case, you standardize X bar, right? So you use a Z value, right? So when you transform X bar to Z, right? You need to know something about standardization, right? Remember that the z is the you use when you transform x to z, you use the relation between x and z like this, right? Now, if you transform x bar to z, you use a mu of x bar and sigma of x bar, right? So you use this, okay? Now, it turns out that mu of x bar is equal to mu, okay? And sigma of x bar turns out to be sigma of square root of n, right? You use this. This one comes from the central limit theorem, okay? Which is one of the most popular theorem in statistics, okay? Now let's talk about central limit theorem. Remember that you take samples from population, right? This is population, and you take sample and you compute x bar, and you take another sample and then you compute x bar. You'll have the different values for this, right? And you take another one and you compute x bar, and like that. It turns out that x bar 1, x bar 2, x bar 3, and you take samples and you have different values for the x bars, right? It turns out that this one is normal, the distribution of x bars, right? It turns out that this one is normal with mean of mu and variance of sigma square over n, right? That's the central limit theorem. Even though we have some kind of condition like n is greater than or equal to 30, right? But even if n is less than 30, right? This theorem still holds, right? So that's the central limit theorem, right? Now, so once you get the test statistic, right? So you need to make a rejection rule, right? The rejection rule depends on the level of alpha, right? Let me show you this, this graph, right? If you set alpha is 0.05, okay? The rejection rule is like this. If test statistic is greater than, right? This z value depends on the alpha level, right? This value comes from the standard normal table, right? If alpha is 0.05, the z value is 1.645, right? So if test statistic is greater than 1.645, and then you reject the hypothesis, right? If you set alpha as 0.01, then you have different z value for that. In that case, z is 2.33. So in that case, if test statistic is greater than 2.33, you reject null hypothesis, right? That's the procedure of doing the hypothesis testing, right? So, your conclusion depends on the level of alpha, right? So when you do the research, right, you have to specify the alpha value, right? Now, let's talk about the p-value. As I said, the computer only gives you the p-value when you do the hypothesis testing, right? So you need to know what the p-value is, right? P-value is the smallest value of alpha for which you reject null hypothesis, right? Let me show you this. So if you have, test statistic value like a 2.20, right? This is the test statistic. The computer computes the area. This, the red area here. Computer computes this area, right? This is a probability, right? In this case, b value is 0.0139, right? Now, think about this. If test statistic is 2.20, all right? And let me draw a graph like this. So this one is test statistic, right? Test statistic 2.2, right? Now, suppose alpha is this, right? Then you don't reject the hypothesis, right? Now, suppose alpha is this, you still don't reject null hypothesis, right? Now, what about the alpha is this? Then you reject null hypothesis, right? So, in this case, the smallest alpha for which you reject null hypothesis is this. So, okay, let me draw this one again. So smallest alpha for which you reject null hypothesis, like just left of this line. So you compute this area. That's the p-value. Okay. So what computer does is to compute test the statistic first, and then find the area. Okay, like this. All right. So that's the p-value. So that means what? If your alpha is greater than this p-value, right? Suppose your alpha is greater than this area, then you reject null hypothesis, right? So from this, you know that p-value, if p-value is less than alpha that you set, right? Then you reject null hypothesis, right? That's the critical here, right? That means, if p-value turns out to be, let's say 0.03, your alpha is 0.05, right? Then you reject null hypothesis. Okay? That's critical, right? So smaller p-value means what? You have good results because there is a good chance that you reject null hypothesis. Rejecting null hypothesis means what? You are accepting your alternative hypothesis, which you support, right? Let me go back to the this graph. Right. As we have seen, the rejection region is at the right side of this graph, right? The reason that we have the rejection region is located at the right side is that, remember that if x bar is pretty big, right, then you are going to support this one, right? And then you are going to reject this one, right? The rejection reason is for rejecting null hypothesis, right? So if X bar is big, then you are going to reject null hypothesis, right? So that's why we have rejection region at the right side of this graph, okay? Now let's go to the another example of hypothesis testing where we have less than, okay, and the alternative hypothesis, right? In this case, if X bar is small, then you are going to reject the hypothesis, right? So that's why we have rejection region at the left side of this graph, right? So, and also the rejection region depends on the size of alpha, right? For example, if alpha is 0.01, then you have z value of negative 2.33, right? Remember that the normal curve is symmetric, right? So if you have 0.01 at the right side, okay, if this is 0.01, then this value is 2.33, right? Since we have the rejection region is located at the left side of this graph, this z value is negative, right? At the center we have 0 here, right? So we have a negative value here, right? And in this case, if you your test statistic is less than negative 2.33, you reject the hypothesis, right? So that's the only difference, right? So for example, in this case, if the test statistic turns out to be negative 2.67, then negative 2.67 is located left of the negative 2.63, right? So you reject the null hypothesis, right? Now, in this case, then what is the p-value here in this case? Remember that the computer computes test the statistic first, right? And then finds the area, in this case the red one here, right? That's the smallest alpha, right? For which we reject the hypothesis, right? Once you find the p-value, right? You apply this, you know, if p-value less than your alpha, right? Then you reject the hypothesis, right? Now let's go to the another one. So if you have a not equal here, right? So for example, you know, you have a hypothesis like this, right? In this case, right, the rejection region is located at both sides of the curve, right? So let's see here. Now, the reason that we have the rejection region at both sides is that if, you know, X bar is big or small, then you are going to reject the hypothesis. That's why we have rejection region is located at both sides of the curve, right? So in this case, when you decide the rejection region, you have to split the alpha in half, right? So if you have alpha is equal to 0.05, and then you split this one in two, so you have 0.025 in each of, you know, two sides, right? So 0.025 in this case, right? and then you find the z value from the standard normal table, right? And then you compute, test the statistic. And if, test the statistic belongs to the rejection region, and then you reject null hypothesis, right? Now, what about the p-value in this case? So you compute the test statistic first, and then you find the red area here, right? Now, in this case, you have two red areas, right? So you have to add, these things, okay? So since these this graph is symmetric, right? So you find one red area and then you multiply it by 2, right? So you get the p-value here, right? The making conclusion is the same as before, right? If p-value is less than alpha, you reject null hypothesis. Okay. So that's the critical right thing here. So you should not forget this, right? If p-value is less than alpha, then you reject null hypothesis, right? That means you accept, right, your alternative hypothesis, right? That's good news, right? Now let's talk about the t, right? Remember that the z was like that, right? So you use this relationship, right? The problem of using this is that sigma is the population parameter, right? That's very unrealistic, when we assume that we know the value of sigma, right? So that's why instead of using sigma, right, we need to use a sample standard deviation, right? So let's denote sample standard deviation as S, right? So we need to use sample standard deviation instead of population standard deviation, right? So in this case, if you use S instead of sigma, that's called the T, okay? This is the T, right? So instead of using, standard normal, right? We need to use T, right? T looks like, standard normal, right? T also has a symmetrical, shape, right? But slightly different from the standard normal because T depends on the degrees of freedom, right? So this one is T, okay? But you don't need to worry about these things because once you put data and then you use the statistical package for hypothesis testing, the computer automatically use T, right, instead of Z, right, and then compute the areas, right, and then the output gives us the p-value, right. Once you get the p-value, remember that if the p-value is less than alpha, you reject the hypothesis, right? So you don't need to worry about this one too much, right? The logic behind the hypothesis testing when sigma is unknown is the same as before, right? So let me draw T here. Okay, T looks like the normal, curve, right? Suppose you have inequality like this in the alternative hypothesis, right? The rejection region is here, okay? And this one is decided by the alpha, right? Okay? And this is t, okay? Depends on n minus 1 degrees of freedom, right? And the alpha, right? And this one is 0. So once you find the rejection region, and then from the t table, right? And then you compute test statistic, right? And then you compare your test statistic with the this critical value. And then if test statistic is greater than this one, then you reject the null hypothesis, right? As I said, you don't need to worry about this one too much, because you are going to use the sample data, right? You are going to put your sample data in the computer, and the computer gives us the p-value, right? So only what you only need to know is to interpret the results, right? Remember that. I'm going to repeat it again. If p-value is less than alpha, then you reject null hypothesis. That means you accept your alternative hypothesis, your research hypothesis, right? I think that's sufficient for today's class. So let's stop here and see you next time.